This is the screencast for section 4.6, example 1. Related rates. Related rates means that, well, up until this point, a derivative function may have only had one thing changing in it. Now we're going to have a couple of things changing. So for example 1 here, assume that the radius r of a sphere is a differentiable function of t. So r is a function of time, and it says, and let v be the volume of the sphere, and volume is a function of time as well. Find an equation that relates dv dt and dr dt. So what they're saying is, the volume of a sphere is 4/3 pi r cubed. But now they're saying volume is going to change according to time and radius is going to change according to time. So you have like an f of x and a g of x in here. So the strategy still remains that to do a calculus word problem, you start out with some algebra 2 setup or algebra 1 setup, something basic that you know. So we have volume equals 4/3 pi r cubed. It's just now in this case volume is a function and radius is a function. So now when we take the derivative to find out how these change in relation to each other, how their rates are related, the derivative of v is dv dt, so the volume is changing according to time, and that's going to be, let's see, 3 gets multiplied as a coefficient now, so that's just 4 pi, leave r of t alone, and now it's squared. I'm kind of doing the chain rule on r of t, so I'm taking care of the cube, or the exponent first. Now I need to multiply by dr dt, the derivative of that function, which I don't know what it is, but I can express it as dr dt. So here is an equation that relates dv dt and dr dt. There is almost a third variable in there in that I have to know what the actual radius is at a specific time as well. Part B, assume that the radius r and height h of a cone are differentiable functions of t. So you've got r of t and h of t, and let v of t be the volume of the cone. So you've got v of t as well. Find an equation that relates all three of them, dv dt, dr dt, and dh dt. So we're going to see how the change in volume, change in radius, and change in height are all related. So first we're going to set up the volume of a cone, which is v equals 1/3 pi r squared h. Now each of those v, r, and h are functions of t as given by the instructions. So now I have to use a couple of things. I have to use product rule, and when I'm taking the derivative of r, I have to use chain rule as well. The left side's pretty easy. The derivative of volume, whose input variable is t, is going to be dv dt. Now over here, I'm going to leave the 1/3 pi out in front so that doesn't confuse me. Next inside, alright, I'm going to take the derivative of the r piece first. So that's 2r of t now to the first power, but then times dr dt because of that chain rule. I have to take the derivative of that r function. Leave h of t alone, plus, now r of t squared stays the same, and now I have to take the derivative of h of t, which I don't really need to use the chain rule, even though I kind of already am. It's just dh dt. Now you could go ahead and simplify that all you want, but again, simplification when it's not necessary could lead to points off if you made a mistake that you didn't even have to do a step for. So I'm just going to leave it like that. The now try problem number 3 is going to kind of create a visualization for us for related rates. It says the radius r, height h, and volume v of a right circular cylinder are related by the equation v equals pi r squared h. So now in part A it says how is dv dt related to dh dt if r is constant. So if your radius is staying constant, which means this right circular cylinder, the radius is staying constant, but the height is growing, and therefore the volume is growing as well. So volume is a function of t, pi r is not, so r squared is a constant, but h is a function of t. So when I take the derivative of v of t is dv dt equals, now remember, r is a constant, so pi r squared, that is just a constant out in front. Pi r squared, that radius is like always 3 or whatever it is, times the derivative of h then would be dh dt. Now in part B, it's asking us to find the relationship of the rates dv dt and dr dt if h is constant. So the height of this circular cylinder would stay the same. So the height is fixed, but the radius is going to grow, and therefore so is the volume. Now I'm not the world's best artist, but hopefully that looks something like, I don't know, a flat donut. So the height is staying the same the whole time, but the radius is growing. So I start out again with the same relationship, but volume is a function of time, and now this time r is a function of time. H is not. So pi and h are constant, so when I take the derivative, dv dt equals pi and h, the constants can stay out in front, and now I need to use the chain rule on r of t squared. So that's going to be 2 r of t now to the first power, and then times the derivative of r of t, which is dr dt. Now our third situation, how is dv dt related to dr dt and dh dt if neither r or h is constant? So everything is a function of time. Everything is changing. Nothing is staying the same. So volume as a function of time equals pi r as a function of time squared times h as a function of time. So now I'm going to take the derivative, which means very much like one of the examples, I'm going to have to do chain rule and product rule in here. I like leaving the constants on the outside just because it gets a little messy if you don't. So I left pi on the outside, and now I'm going to do product rule with r squared and h. So that's 2 r of t, and then now to the first power, but then dr dt, times h of t, left h alone, plus, now r of t squared stays normal or original, and then h of t gets its derivative, dh dt. So now what does that look like? Well, everything is growing. So our original right circular cylinder, its height is growing, its radius is growing, so it is just getting bigger in every direction. So the whole thing is expanding, kind of like I don't know, one of those little toys that you have in the little capsule and you put it in the bathtub, and then after it pops out of its little capsule, it just gets bigger and bigger and bigger. So it's expanding in every single direction. Or a marshmallow on the grill. I don't know, I could go for some more right now actually.